So hi, everybody. Thanks for being here. This is the pathway presentation today, and you're going to hear from Professor Trevor Thornton in the physical electronics and photonics area. And then when he's done, we'll hear from Professor Keith Hulbert, who's in the electric power and energy systems area for EE. But we're ready to go, and Professor Thornton, feel free to take it away. Thanks for being here.
Very good. Well, thank you, Bob. Thanks everybody for taking time this morning. All right, so I'm going to put it in presentation mode and then share my screen. All right, do it the other way. Let's go to share screen. There it is, share. So now if I put it into presentation mode, tell me, Bob, do you see my full screen or the slides notes page?
No, it's good. I see the full presentation.
Okay, very good. So yeah, thank you everybody. Physical electronics and photonics is a bit of a mouthful, isn't it? I always find myself stumbling over that like a tongue twister. So basically, it's everything to do with semiconductors and related materials and transistors and devices. And a lot of it is kind of wrapped up in this big picture view that I have here of the Waymo self-driving car. We see this all the time, don't we, on the Tempe, Scottsdale area. They have a permit to drive these things around, and we sort of trust it implicitly, right? So it's full of computers, of course. Those computers are performing all the feedback and control that allows these things to maneuver without running us over. And then, of course, it's full of sensors. You can see LiDAR and optical sensors mounted all over this monster. And then the communications to make sure all of that data is reliably transferred back and forth over the cloud. And then, of course, power management. These things have chips that consume tiny amounts of power to electric motors that run on, what I think, 480 volts and high currents. So this self-driving car kind of personifies the state of the art for semiconductors. And that's really what the physical electronics program tries to address, the components that go into something like the Waymo car to make it self-driving. And just a little bit of history, right? So during the Second World War, vacuum tubes, middle of last century, were being developed for radar and some kind of very basic computation. And then in the 50s, people started building semiconductor devices out of germanium, common semiconductor in the day. So here's the first bipolar junction transistor manufactured at Bell Labs. And this thing is macroscopic. You could build it on your kitchen table, just one transistor. And then Texas Instruments, Kirby and his colleagues demonstrated the first integrated circuit. This thing has a voltage controlled oscillator, what else? Forgotten. A couple of other circuits on there. And again, you can see this thing is held at the Smithsonian Museums in Washington, D.C. It's one of their rotating exhibits. So if you're ever in Washington, go to the Smithsonian, you can see this thing. It's sort of millimeters and centimeters in size. And then, of course, rapidly moving forward, we're now at the age where companies like NVIDIA are the most valuable company on the planet, building these advanced AI chips that go into everything. A few examples here. I should point, right, NVIDIA, because of the fears that the Chinese had developed a cheaper AI model, NVIDIA shares lost $600 billion in one day. 600, so that was kind of 17% of their net worth, that largest drop in value of any company ever reported. So it just shows you how important these materials are, right? $1 trillion companies based on manufacturing these advanced chips. Of course, we've all heard of Moore's law. I think the next slide is probably the better picture. Yeah, here we go. So number of transistors on a chip doubling every 18 to 24 months. And so here's a plot here. Gordon Moore noticed this back in like 1974 or something, when there were just 3 generations, and he very presciently projected it forward. And his his law. Okay, it's not a law like Einstein's first law, F equals ma. It's a sort of empirical observation that the number of transistors doubles every 18 months or 24 months. So look at how, let's count the zeros here. 1,000, a million, a billion, a trillion. So we are looking at 1 trillion transistors per chip before the end of this decade. So kind of phenomenal. So the manufacturing expertise that underpins this is enormous. And really, that's what we're trying to do in our PEP classes, explain to people how all that functions. So I think, yes, electronic systems driven by semiconductor chips, that Waymo self-driving car is a good example of that. And, you know, this, I'm not sure this classification is going to hold much longer. We used to talk about analog chips, and then we talked about digital chips, and then we kind of separated. Then we joined them together to have mixed signal, both analog and digital. But now these chips are so complex. They contain analog, digital, memory, optimized for neural network applications for those AI chips, power control. So really everything is integrated on the same platform now, and it's only getting more complex. So to have a career in this semiconductor manufacturing industry, we need to understand how semiconductor devices are designed, how we make them, how we measure them. If you've got a chip with 100 billion transistors on, how can you be sure that each one's going to work properly? You can't measure them individually. So we have to have a lot of modeling, have to have a lot of good statistical analysis, and then people need to sell these chips. So there's marketing and sales. So all of these things are very, very rewarding careers that are underpinned by this physical electronics and photonics. So we need to know, and this is what we focus on. We don't focus on marketing and sales at ASU. That's not our job. So instead, we teach device physics. How do these devices operate? Once you understand how the devices operate, how do you combine them to have the circuit function that you're interested in? Once you design the circuit, how do you fabricate them? And then modeling. We talk a lot these days about combining both the modeling and the device and circuit design in a sort of closed loop. So we need to model the devices, we need to model the circuits, and we even model the fabrication processing steps these days. And then ultimately measurements. You know, the measurements are very challenging. These devices are tiny, they use tiny amounts of current, or they use huge amounts of current if you're in the power field. And they're very fast. So sometimes the devices are faster than the machines we have to measure them. So these are all the kinds of things we need to address. So we put together an excellent suite of courses for you. So I'll just go in numerical order. So 434, quantum mechanics for engineers. Okay, little timeout. Don't tell the dean, but all my degrees are in applied physics. So back in the day when I was a young person, like all the students today, I was looking at how you could apply quantum mechanics to semiconductor devices to understand how they would operate in the future. And nobody really worried too much about quantum mechanics on a day-to-day basis. So this was in the realm of physics. But now our cell phones depend on these rules of quantum mechanics. So now we teach it as part of the engineering discipline. So 434, it's the basic physics. See, there's that word physics, describing the behavior of electrons, atoms, and the materials that they reside in. So quantum mechanics, and then EEE 435. This is the class that I teach. And see, look, I didn't put important there, somebody else did. But this is important because it gives you a hands-on fabrication experience. So we take students into our clean room on campus, and we look at the unit process steps. So diffusion, oxidation, deposition, etching. So all these basic individual steps that we then combine together when we make a CMOS. So of course, complementary metal oxide silicon semiconductor. And then MEMS, right? Micro electromechanical systems. These are very important. We have MEMS components in our phones and other devices. 436 underpins much of what we do in 435. So you've all done 352, that's our properties of materials. And so that explains the differences between metals, insulators, and semiconductors. And we finish 352 by looking at how a PN junction diode works. And then 436 takes up from 352 and looks at how, basically finishes with how metal oxide semiconductor field effect transistors, or MOSFETs, operate. So the explanation of how both diodes in more detail as well as transistors, particularly FETs, work is covered in 436. And then the sort of sister course to that, 437, 436 focuses on electrical devices like diodes and transistors. 437, by its name, focuses on optical devices, so light-emitting diodes, lasers, photodetectors, photosensors. So how do those devices operate and how they built upon semiconductors? Then 439, semiconductor facilities and clean room practices. So if you're going to be the manager of a clean room facility, which is a huge responsibility, you need to understand how those semiconductor manufacturing foundries are built, managed, and maintained. And of course, that's very important now. If you drive along the I-17 corridor on the west side and you look out west in the horizon, you'll see all these cranes where companies like TSMC are building the latest $20 billion clean rooms to build their 4-nanometer FinFETs. All right, then of course 465, very related. So if you think about optoelectronics, we have LEDs and photodetectors. So photovoltaic energy conversion, so PV, that depends on a PN junction diode absorbing light and generating electrical current as a result. And so this class 465 explains, as it says here, the science, manufacturing, and economics of solar energy. So I know we typically have time at the end to ask questions. So if you want to post questions in the chat, somebody will be addressing those. So Bob, any questions as I'm about halfway through?
I don't see any questions yet. I
Okay.
personally had a question is, when you showed the picture of the Smithsonian early transistors, do
Yes.
Folks like you think it's beautiful? Because it kind of looks hideous.
It does look ugly, doesn't it? I do. I think somebody should make a coffee table book about how the latest transistors are made, because those are just gorgeous images to look at. So the faculty who teach these classes are involved in a lot of state-of-the-art, cutting-edge research. I'm just showing a few examples here. So a colleague of ours demonstrated the first white laser. It's actually on the same chip, it's a blue-green-red laser, and the light is combined to produce what the eye sees as a white light. And that's important for high-intensity, high-contrast televisions, right? So we have LED TVs. Someday soon, we might have laser-based TVs using these white lasers developed at ASU. I mentioned the course about solar cells. ASU has, a world-leading capability down at our science park for manufacturing, testing, modeling solar cells. We have the nanofab clean room. This is the space where students taking that class 435 get trained. Here's Carrie, our photo engineer, working on the OAI optical aligner. And then recently, my interest and a bunch of other faculty at ASU, we're looking at these wide bandgap power devices. So silicon has a band gap of about 1 electron volt or so. We're currently working on diamond, which has a band gap of just over 5 electron volts. So it can withstand these enormous voltages, 10 megavolts per centimeter and currents of 100,000 amps per square centimeter. So lots of exciting things happening with diamond and related materials for this, to basically build the power infrastructure of the future that we need if we're going to have all this solar and renewable energy. So, all right, so lots of jobs, a huge variety of jobs in the semiconductor industry. So I often joke with people that companies like TSMC and Intel, they hire from all of the schools within the Fulton Schools of Engineering. So they need engineers, they need electrical engineers, they need computer engineers, they need mechanical engineers, they need chemical engineers, they need material science engineers. So basically, all the engineering and science disciplines are represented in these companies. So circuit design, you do this in your circuits related classes. How do you build an integrated circuit? How do you lay them out so that they operate efficiently and at low cost? We have classes on simulation and modeling. Excuse me. People work on simulation and modeling within these companies. There's a new term that is been adopted called the digital twin, and so this is really a top level view. You have a $20 billion factory, and you can simulate everything that's going on inside that factory with its digital twin. And so if you're an engineer, you may rarely step inside the factory to run the tools that you're responsible for, because you're actually running those tools through their digital twin, which allows you to do simulations of how they operate, what the product yield is going to be. So very complex simulation and modeling. So not just at the semiconductor device circuit, but entire, a large chunk of the entire factory. All right, device fabrication. You need to know how those tools fabricate the devices and how changes in the tool impact that fabrication. So a lot of scientists and engineers spend their time looking at yield, maximizing yield, because that maximizes profits. And then I mentioned earlier, right, measurement and characterization. If you're building a 64 gigabyte memory chip, how you can't test that they're all working. So you have to have complex testing procedures, modeling, statistical analysis that allows you to do that kind of characterization that allows your company to guarantee that that product will last 10 years. And then finally, sales and marketing. You're in the company and you have the latest, best component, but how do you get that out there to the people who could use that? So sales and marketing people need to have a good technical understanding of the products that the company's offering, whether that's a chip itself, or the equipment that makes the chip, or the software that helps you simulate the chip. So lots of opportunities there in sales and marketing. So here are just some pretty pictures. Look at this one here. This is the ASML extreme ultraviolet lithography patterning system. So this costs, I don't know, I'll make up a number, $100 million, $200 million. So a huge expense. New York Times had an article a couple of years ago. They called it the most complicated machine ever made. And this is the thing that is now export controlled. The US government has prevented this from being sold to some of our competitors. So lots of interesting economics and geopolitical stuff going into this industry. I tell all my graduate students, I tell everybody, in fact, this is a great time to be working in semiconductors. The Biden administration recognized, and it was before that actually, this is a discussion that's been going on over a couple of administrations, but it resulted in the funding of this CHIPS and Science Act. 50 billion of that went to companies like, as I mentioned, here's TSMC in the West Valley, here's Intel building new factories as a result of these loans and tax policies that came out of the CHIPS and Science Act. But close to 2 billion of that also went to the Department of Defense to do university-based research. So all of this has the goal of bringing semiconductor manufacturing back to the continental US. The United States invented the transistor. We invented all the early integrated circuits. And then gradually over the last 10 years, a lot of that expertise moved offshore, primarily to the Asian countries. So the goal is to invest in the United States and bring that back. And that investment is building new factories. Those factories will need, advanced science and people with advanced science and engineering degrees, technicians, the whole gamut to make them work. So again, lots of opportunities. And so there was a time when Intel would have that Intel Inside advert on the television. And so everybody's heard about Intel. Fewer people have heard about Global Foundries. We know about Samsung because they make a lot of our products. NXP, there's dozens, if not hundreds of companies that actually manufacture chips. Some well-known, some less well-known. We also have the whole supply chain that supports these companies, right? So we have the equipment manufacturers. Applied Materials, they're a big one. There's a big announcement end of last year. They partner with ASU, a $200 million investment to put their most advanced tools into our clean room down on the ASU Science Park. ASML, they're the people who made that advanced stepper. Here's a picture inside that extreme ultraviolet lithography tool. People like companies like Keithley, eSight, they make the instruments that you use to measure the chips. And then you have the other, hundreds or more service companies that provide, for example, the simulation software, as well as, complex other services. So there's a whole breadth of industries that most of the public have never heard of, but have these rewarding, well-paying jobs. So I know most of you are in the, your juniors and seniors, so you're thinking about finishing your bachelor's degree. And I'm sure Bob and his colleagues will have given you the opportunity to understand our master's degree. So, and then finally our PhD. And then I'll just show this slide. So this is from 2023, so fairly relevant. So this just shows, as you might expect, the salaries increase somewhat, going from associate degree to bachelor's degree to master's degree. Not sure what a professional degree is, but PhD. And then the unemployment rate. This is one thing I've noticed. It's very unusual for these companies to let go of their PhDs because it takes so long to hire them. So just something to think about. And I think I have one more slide. Yeah, so question, why don't we finish there? Thanks, Bob.
Yeah, we do have a couple of questions. Thank you for that. You did touch on Raphael's question in here, but he's asking, maybe you can speak a little bit more on that he's heard about the semiconductor industry being one of the most competitive within the electrical engineering area. First of all, is that true? And do you have anything else to comment on that?
So I don't really know. I don't know. When you say competitive, does that mean they are, it's hard to get jobs?
I would expect it's like I would interpret it for the rest of him and his growth, and people are competing for employees.
Oh yeah, well that's for sure. I mean, some studies have shown that over the next 5 years, the semiconductor industry is going to need to hire anywhere from 50 to 70,000 engineering technicians and scientists. So yes, lots of opportunities. Yeah, maybe that's the question. So then motion. First year EE student. Oh, I see. Good. You've joined us very early. So I always encourage people to look for internships. This is a very good way to get experience with that particular company and the industry more broadly. So Motion, you're probably a little bit too early to start applying for internships. I would suggest at the end of your sophomore year, start applying, then maybe you can spend that summer and the following summer before your senior year. So certainly applying for internships is very valuable. And then I'm sure Bob's talked about this. Yes, undergraduate research opportunities. The Fury program is a great way to work with a faculty member on a research project. And a lot of if you have an interview with one of these semiconductor companies for either an internship or a job, they'll be very interested to know what you did for your undergraduate research. So that's a good way to get a foot in the door as well.
Yeah, I also have an additional comment that really as a early undergraduate, because we often have freshmen and sophomores joining us for these, which is awesome. It's really my advice is you to treat this like a habit that you are forming. So you are not prepared necessarily to dive in and do a high level internship or do, PhD level research. But you definitely have opportunities to prepare for doing that through engaging in the Fulton programs like Fury and EPEX. I'll put the link to all these things in there. But it's really forming a habit, and that also includes studying, and then if potentially even reading a book outside of required materials on the things you're interested in. Anything to kind of get your brain thinking in the language of EE will lead you towards a future in it, is my thought.
Well, very good, Bob. If there's no other questions, I'll pass the baton over to Dr. Holbert.
That would be great. We really appreciate you taking the time to be here, and I'm sure the students thank you too. Any books you recommend? We'll do a book list at the end. I have some popular books, unless Professor Thornton has any books in mind.
There's so many. I'm sure you have a good list, Bob.
Yeah, I'll put a list in there. But thanks again for being here, and we'll get a book list for you here in just a moment.
Okay.
Thank
All
you
right, very
so
good.
much, Professor Thornton. Really appreciate it.
Oh, you're very welcome. Thank
Good
you,
to see
Cheryl.
you.
Bye. Bye, everybody.
Bye.
So thanks again. We're going to move on to our second part of the presentation with Professor Keith Holbert, who is a faculty in our electrical power and energy systems area, and he's also developed the nuclear power certificate program that we have at the graduate level. So he's an expert in that area, and we're grateful that you are here today, Professor Holbert. Thank you for your time.
Thank you, Bob. It's good to be here. I want to partially answer or extend an answer to Motion Khan there's question. And this actually would be good for all of you, not just him. But I would tell you, and it doesn't matter what level you're at, be reading the news. If you want to know what you can do to get into an industry right now, make sure you're very fluent, cognizant of what's going on in that industry, so that when you show up, whether it's for an internship interview or for a career interview when you're getting ready to graduate, you can talk the talk, and you can express to the people that you're interviewing with that you're very cognizant of what's going on in that industry. People can make not so good mistakes in an interview. I want to give you an example that happened to someone where I went to school some time ago. I'm going to change the name of the organizations, though, not to give it away. And here's what happened. This student, okay, getting ready to graduate, shows up for the interview. And during the interview, he says, yeah, I really want to work for, I'm going to change the name, Arizona Power and Light. And the interviewer stopped the interview and says, well, that's really great. I'm here to interview people for Arizona Power Corporation. So I'm going to let you go now. He terminated the interview because the student was thinking about the competition. At least that's the words he used. And maybe it was just a slip of the tongue, but it's be aware of what's going on in the industry. And of course, who are you interviewing with? Well, with that said, let me go to the slides here. You should be able to see my title slide here at this point. Great. So I'm going to talk about the electric power area. Again, I'm Dr. Holbert. If I can get it to work. So a little general information here about the power area, if you will. It turns out that as far as at ASU, we have one of the larger, in fact, the largest electric power and energy systems program in the U.S. When you think about the kind of classes and research that's going on, it's an extremely diverse group of people. simulation tools as well as experimental facilities. And if you look at some of the statistics, turns out that the ASU program is one of the top 3 programs in terms of research excellence and recognition. This leads to the fact that the reputation for ASU graduates is high if you're headed off to graduate school here or somewhere else, as well as heading off to the job marketplace. Another thing to know about the power area is it's one of the more difficult areas to outsource jobs. It's hard to put a power job in a different country that might be a lower cost in terms of personnel expenses. So that's good news. And of course, we also know that climate change is occurring no matter what particular group is running the government, and the utilities respond to that. They're making changes with climate change in mind. So who are members of the power faculty? Well, I'm not going to go through the entire list, but I am going to tell you the reason for showing you this list. Except for the 2 individuals who are emeritus faculty, eventually at the senior level, would like perhaps to end up with a power senior design project. And so this list of individuals, these pictures, are faculty members who certainly can guide those power area projects. I'm going to talk more about each of these courses, but I want to go ahead and give you the list of power area courses right from the start here. There's the junior level EEE 360 class. That's the Energy Systems and Power Electronics. This is really an introductory class towards thinking about transmission, distribution, utilization type of careers, if you will. Then there's the 2 4-6X classes, which I happen to teach. The Nuclear Power Engineering 460 and the 463 Electrical Power Plants class. And again, I'm going to talk about all of these classes in more detail. The 4-7X classes include Electric Power Devices 470, Power System Analysis 471, Power Electronics and Power Management 472, and the Electrical Machinery 473. All of these courses are really available as ASU Online or iCourses except for the 473 class. So one of the things available to you is a concentration within electrical engineering. So you could get essentially an extra stamp is how I view it. Bob and other advisors may view it a little differently, but I think of it as an extra stamp on your diploma. So what are those requirements to get that extra accolade, if you will? Well, you need that junior level class, the EEE 360 class rather, the Energy Systems and Power Electronics class. And then you're going to need at least 9 hours of EE technical electives that are in the power area. And that's why one of the reasons I gave you those classes on the prior slide. So you can go through and basically, since they're effectively 3-hour classes, you need three of those courses. Occasionally, though, there is the possibility of taking a special topics, a EEE 498 class that from time to time are offered. So that's an option too. And then finally, and this is very important, you need to have a senior design project that is in the electric power systems area. Now, probably in most cases, the easiest way to achieve that is through a senior design project being mentored by one of those faculty members because they're likely guiding projects in the power area. But it's not an absolute requirement because you might be working on something that's being offered by a controls faculty, for example, and it turns out that one aspect of the project is very power intensive. So that also could be a possibility and still count. So then you got more than 9 hours worth of classes to choose from. So how do you make the choice? Which power class should you take? Well, I think about these power classes being divided, and the rest of the faculty do also, being divided into three areas. First of all, there's power generation. Second, there's transmission and distribution of the electricity, the power being produced. And finally, there's the utilization of that electricity in certain machines area. And you can see the little diagram at the bottom of the slide showing this progression, logical progression from the generation of the electricity to the utilization. So when you think about power generation, we'd like to be talking about things like the power plants making electricity, as well as renewable resources. This could be distributed generation, like you see the solar photovoltaic on top of roofs and buildings of residences, as well as power markets. Then transmission and distribution. This includes power systems, high voltage engineering, the protection of those power systems, and as well as the control of those power systems and the distribution systems. And finally, that electricity utilization includes things like power electronics, which is really, in my opinion, a hot area personally. The machines, electric vehicles, control even from that standpoint for the utilization. So here's a simple or two simple examples of all three of those areas. If you look at aircraft as well as ships, they certainly need to, they're an independent island, if you will. They're isolated. So they have to generate their own power. So there's the generation side of the equation. And then now the power has to be distributed throughout the ship or the aircraft. And then finally, that power is not just sitting there, it's being utilized for something, maybe motors, maybe lighting. So going back to one of my comments before I started this, being cognizant of what's happening out there, watching the news, well, renewable energy is, of course, a hot topic. People are turning to wind and solar for sure to some extent, but we find that as the amount of wind and solar goes up, and California is a good example of this, as those resources are utilized more and more, it has impact on the power systems themselves. Like in California, it's the famous duck curve, which I don't have time to talk about this morning, but it essentially is because of all the solar, there's a big rise in electricity production by solar on top of roofs in the afternoon, but suddenly the sun goes down and that electricity is gone, at least that generation mode. So there's unique issues that occur due to renewable energy, as well as you need storage. That's a big issue too, electricity storage. So thinking about that power generation, what classes, if you're interested in power generation, might you take? Well, there's the EEE 463 and the 460. The 463 electrical power plants class, this really, and I teach both of these two courses, this really looks at the generation of electricity from all sources, the renewable, the fossil may be, quote, going out of style, but they're still building a lot of natural gas power plants today, for example, and there's still a lot of coal-fired units out there. Not as much things like geothermal, for instance, but we still address those. We look at thermal cycles in that class, which kind of sounds old at first, but when you start realizing, well, there's solar thermal and geothermal, there's ocean thermal, it's still very applicable today. And then an important thing that sometimes we forget about, economics. Okay, engineering decisions, economics drives those decisions. Then there's the EEE 460 class, nuclear power engineering. Nuclear is coming back seemingly with all this AI stuff because people like Microsoft and Facebook, Amazon, they all want to power those AI and those data centers, and they want it to power them with non-carbon emitting power plants. And so the way to do that 24/7 is through nuclear power. One of the reasons some individuals are attracted to power engineering is because there's a lot of application here. It's not all theory. So keep that in mind. If you're a hands-on kind of person or wants to do things where you can really see what's going on, power may be an option for you. But continuing with those three areas, the second area, transmission and distribution, the EEE 470 electric power devices, this is really thinking about what's going on in the transmission and distribution system in terms of, I think about it in terms of control for a great deal. That is, at least it's the devices that are doing the control. Things like, as shown on the slide, circuit breakers, relays, voltage and current transducers, which really are fancy names for instrumentation to be able to read out, oh, here's what the current is, here's what the voltage is. Also protection devices. EEE 471, power system analysis. Now you're taking a look at the actual transmission line, trying to determine, okay, is everything going well? Do we have a fault? What's going to happen if there is a fault? What happens when there's a short circuit? Take a look at the power flow. This definitely brings in the controls aspect. And I'll pause there about controls for a second and say the following, that you're probably not going to take all your tech electives in the power area and you're going, okay, well, how do I make a cohesive unit with other areas, for example? Well, there's a controls class in the controls area. What if you're really interested in the control of power plants or the control of the power systems? Maybe it would do you good to take a controls class out of the controls area, right? It makes a perfect cohesive unit there. And so I mentioned power electronics being a kind of a hot area in my opinion. Here's some examples of things that we see in the power electronics area. There's, well, Google Data Center. Down in the bottom right, electric vehicles. That's certainly, whether it's a purely electric, whether it's a plug-in hybrid or just a hybrid, I think you can see just from, again, reading the news, that there's a lot of interest in that. Smart appliances, energy efficiency. Maybe you've got Google Home Control, for example. So a lot of different things going on in the power electronics area. So finally, the third area, electric energy utilization. EEE 472, there's that power electronics and power management. So you're getting the fundamentals of the power electronics. You wanted to be able to analyze, for instance, power electronic converters. I mean, how do you change efficiently? How do you change AC into DC and DC into AC without just using a simple old bridge, for example? So this certainly brings in things like electric vehicles and even the renewables, because a lot of advancements for wind power have been made through power electronics at definitely a larger scale. Moving down to EEE 473, electrical machinery. Okay, well, you know, if you've driven an electric car, starting to think about that, well, that's electric machinery. So in looking at that and thinking about that electric car, and some I've driven a couple of different ones. One I didn't so much enjoy, but the point is you would like to recoup some of that energy, recharge the battery. So there's that regenerative braking. But I would like the regenerative braking as a consumer, a user, to be seamless. I don't want the quick, harsh stop and start from that standpoint. But there's a lot more different electric machinery. There's a power plant level, synchronous machines, those conventional, and of course, making power from things like wind. And then there's senior design projects. I'm not going to really go through this list and just say that there are senior design projects in all the different areas. Power generation area, there's can be transmission and distribution based senior design projects, and of course the utilization. But these are just some examples that show that in fact there's lots of different possibilities. But one thing I want to say about this, especially for those who haven't been in senior design or wonder what do you do in senior design, and that's why I don't spend a lot of time going through this list and indicating them, saying much more about them, is the fact that this list, what you do available to you, changes every semester. It's not the same old projects. We'd like to give you projects that are current, interesting, what's happening out there in the industry. So keep that in mind. And of course, you want to find some friends, some peers when it comes around to senior design, if you can, and group up in like a team of 4. Here's one of the things going on in the power industry area. Historically speaking, generation has been centralized. There's these big power plants making electricity. But one of the things going on with the smart grid, which is a paradigm shift, is the use of distributed energy resources, like shown here in that photo, photovoltaics on top of a housing unit, which doesn't have to be a house. It could be a Walmart or other store or an other industrial facility. And then, of course, there is the generation of electricity even by industry, what's sometimes referred to as cogeneration, and that would be distributed. And then down here, inverter based resources. That's back to that power electronics. And so the power electronics here, I want to be able to change that DC, for example, photovoltaic output into AC, which most of the electric power systems utilize. And so integrating that becomes of interest. But here's something, a novel idea. Rather than generating DC and turning it into AC, what if you were able to just use the DC power directly and avoid the power losses because of the conversion? Maybe that would be worthwhile for certain applications. And it in fact is done for some remote applications. One of the things to keep in mind is that there are different research centers at ASU, and one of those related to what we're talking about here this morning is PCERC, the Power Systems Engineering Research Center. Turns out that PCERC is a consortium of 13 universities, and look at this, a huge number, nearly 40, and its number changes as time goes on, different industries, and it turns out that ASU is the lead university. You're at the lead university. They look at all of these different areas, including things like markets, and that's really trading. I think of it as trading electricity. How much do you pay and from one system to another area, market area, that T&D, transmission and distribution. And there's multiple researchers, faculty involved at multiple universities. But one of the interesting things is the fact that the industry is supporting this. This is not a government-supported entity. So these are things that the industry, the people that are going to give you jobs, are really interested in. So those project areas are all through power engineering. Facilities that you might have an opportunity to work in, the power laboratories include a high voltage lab, the power electronics lab that is shown in this photo here. There's electronic control of power systems, a simulation lab, as well as a instrumentation lab. And we continue that list by saying there's, in these two photos, top right, the lab for synchrophasor technology, and at the bottom, a lab for machine learning and power systems. With that, I would like to try to take any questions that you might have, and I'm going to quit sharing so I can see the chat room in case you ask questions there.
Yeah, thanks very much. There are a couple of questions in there that you touched upon, but I'm sure you might have additional comments.
Okay, let me go and see if I can. Okay, first question I see, that's next. Didn't we send almost $1 billion to nuclear here in the States? If I remember correctly, it should be growing industry for the next bit. I would say the big thing for nuclear really is something I stated early on, and that is it's the AI right now. Their interest, if you, again, I tell you to keep up with the news, and it's back to that. Amazon, Microsoft, okay, Meta, as in Facebook, they are all jumping seemingly on the nuclear bandwagon, and they are supporting both reestablishment of some present generation nuclear as well as future nuclear. Now, Tony says, I heard the same. There have apparently been some significant advances for nuclear. Okay, down to Brianna's question. Long-range wireless power transfer systems is an emerging novel technology that's starting to take center stage, and you go on to say all that. Is there any work in wireless power transfer field going on at ASU? I'm actually not aware of any, but I'm going to make a personal comment here and tell you about one of those reading things. And this is actually, well, I'll just tell you about the reading thing. And that is that if you look at what the International Energy Agency says about just wireless power transfer and the efficiency aspect compared to just plugging things in, they're saying we're going to need a bunch of power plants just to make up those energy losses due to wireless power transfer. Now, if I really care about the environment and I want to reduce climate change, maybe I should be personally willing to just plug things in. And that's maybe too strong a comment, but it's true. So I would encourage you to take a look at the power losses. I mean, yeah, and what the ramifications for that are.
Thank you. That's great. That's why we have faculty to really make us think about the things that we hear about, particularly in some people think it's a great idea, but we might not know. I did have a quick follow-up question on the nuclear
But let me
technology.
say one thing, Bob, and
Yeah.
maybe Brianna can make that 99.9% efficient, and she will do the world a great deal of good. Now, back to what you want to say. Sorry, Bob.
Yeah, no, so a lot of I've heard talk about data centers and AI and nuclear. Just so some of us who don't quite visualize, are we talking what we're used to seeing in a nuclear power plant just being brought up, or is it a different kind of
Okay.
facility that generates it?
That's a good question. It's about half and half. About half of the big, huge data center AI organizations are trying to support actually restarting some nuclear power plants that were undergoing decommissioning. So that's just unheard of, never been done before. And then the other half, they're looking at trying to support small modular reactors, for example, and other advanced reactor concepts. So you got a little bit of both. But why are they so interested? I don't know if you read the news, everyone, but when you did a simple Google search compared to today's AI query, that AI query uses about 10 times more power than the simple Google search. So that's why there's going to be the need for a lot more electricity.
I find that fascinating, particularly since if you watch media and sports games like I do, it's almost like we're encouraged to have mundane conversations with AIs that are doing these complex high energy searches. It's really interesting. There's one more question from here from Tony, if you caught that.
Yes, learning about nuclear power generation would be a path forward for fusion power.
Great, students. If there are other questions here, this was an awesome presentation. Thanks for Professor Holbert. If there are other questions, we have just about a minute or two, but these have been great questions and conversation was exciting and lively. So think we might be wrapping up on those, but again, thanks very much, Professor Holbert. That was a fantastic presentation and super interesting.
You're very
Hopefully
welcome.
some students are thinking about power now. Yeah, this recording will be updated shortly. There's an older one. It usually takes us a week or two to get the new one updated. If you scroll up on the chat, you'll see the link for where we're going to put those recordings. But I think we'll go ahead and wrap this one up. Cheryl, if you'd like to stop the recording. Students, thanks for being here again. Thanks, Professor Holbert. That was great. We really appreciate your time. I know you're busy.